after this one, right after this, in general, you have a circuit called readout circuit. So you have to connect this one to a circuit because you want to get the information out, otherwise this information is not usable. So you get the information out, calling a circuit, readout circuit, and then you convert these signal to digital signal. In electrical engineering, we like electrical signals a lot as compared to analog signals, because digital signals are very easy to process. Analog signals are not easy to process. So in general, we get a circuit connected and then we convert it to digital. That's general sensor. Now, what is smart sensor? Smart sensor, we add a processing unit to it. We add a wireless link to it. So you can get the information out through wireless link. So you can actually turn on your cell phone and you see the humidity in this room or the temperature in this room. Because you have wireless link and you have a processing unit. So this processing unit will process the information provided by the sensor. You also obviously have energy source, which is the big problem. I will talk about this one. That's a major problem, major issue. Okay, we want, ideally, if I tell you, what is the ideal sensor? You say, well, I want a sensor that doesn't require a battery. This is ideal, right? I don't want it. The battery is a headache, right? But it's still a major problem. So we will go through this, what we can do for this, what is the effect on this part of the processing, what is the effect on the wireless link. So intelligent one, that's smart sensor. So smart sensor has a processor, has a link, has a power supply. Intelligent sensor is the sensor that can make decision by itself. Okay? So in a situation given, it can decide. So it requires lots of processing power. This is not enough. This is smart, but it's not intelligent. So that's the difference between them. Now, on top, if I ask you, what do you require for sensors? Especially consider the fact, I didn't talk about this one, these sensors will change the life that we know it by, for now. Let's just say I can tell you what would be the effect of smart sensor on our daily life. Everybody uses Google, right? Everybody. Now, I can tell you with these sensors, the next search you are going to do in maybe 5, 6 years from now, you are going to go ask Google, where is my key, my car key? It's going to tell you. It's not the kind of Google search that you are going to do with everything sensor enabled. Okay? This is going to come around maybe that's what we expect in maybe 6, 7 years. Or you can say, who was sitting on my chair? Okay? Ask Google, it will tell you. Because why? Because everything sensor, your chair has a sensor, I have a sensor, I sit on it, information online, available. So it can tell you exactly who was sitting on your chair for how long. So these are the effect of sensors, and we are expect them to be in billions employed in few years. So what you want, the first thing that you want from your sensor is security. You don't want your camera on your cell phone to be available to others, right? And I had another presentation that I opened the camera remotely from another person. So this is possible. They can watch you, they can go in, okay? And I had an app, I wrote it myself. I sent it to someone and I recorded, with his own permission obviously, recorded his talking in his voice and brought some photos from his home back, and then then emailed to him, these are the kind of things that can happen. So it is not secure. So the security is on top of everything, okay? We want the smart sensors to be secure. What you need for this security, you need circuits, you need silicon, you need ICs to make it secure, to implement a strong algorithm for security. So security at the hardware level, security at the software level. This is the top of the thing for our sensors. Now, power consumption. I told you, ideally, I don't want the sensor to require a battery. I want to give you something that's my sensor, it works forever, it doesn't require a battery. Ideal, right? But power consumption, at least at this stage that we are in, we cannot actually bypass power consumption. The other thing that I can tell you, in few years from now, with the billions of sensors, we will deplete of the resources for battery making. That's a very hot topic right now in the research environment for electrical engineering. How to manage the requirement for so many wireless sensors that are going to be implemented. So people are working on low power wireless technology for sensors. Now the cell phones you have, they are not the same Bluetooth technology that you had a few years ago. The battery that they consume is much lower. So I have a sensor actually in my, right now it is with me. It can work for a year, 24/7, with a coin battery, 12 sensor on it. Still not enough. Still we are trying to push it harder to have more information. So imagine 24/7 information online from 10 sensors for a year with a small coin battery. Still we say that's not enough because when you multiply by billion, then it becomes a problem. Now, so these technologies also we are working on. The physical dimension. And I'll tell you that 3D IC, at the end, I will pack them up, what will be the effect of 3D IC on all these requirements. Physical dimensions. For many applications, physical dimension is very important, right? For example, if you have a pacemaker implanted in your body, you want the size of these sensors to be as small as possible, right? You also want the power consumption to be as low as possible, right? The same requirement for wearable electronics. You have a watch. You don't want to actually change the battery every year or every 3 years, right? You want the size to be as small as possible, the sensors too. So they consume less power. You want to also lower the cost of the sensor. That's also important because if I give you a sensor, I say, well, this is $100. It's just, okay, keep it for yourself. Right? Give me something that I can purchase it over just a few dollars, right? So the cost for some applications, not everything. For example, for medical, it's not so cost sensitive. When you are thinking about the pacemaker, it's just maybe a few $100 is not that much important. But when you are talking about humidity sensor, then yes, I don't want a humidity sensor to pay $100 or $200 for it. Then for energy sources, the energy available battery, there are many scientists working on energy harvesting using solar, thermal, vibration, radiation. And now at this stage that we are in, with the light intensity that we have in this room, we don't need a battery if you keep this light intensity. We have enough energy in the room to turn on the sensors. Sensors are so low power right now. So we are thinking about 200 lux. Because we have measured some, I assume that here we have 300, 400 lux. That's more than what is required for a wireless sensor to work forever without the battery. Now, MEMS technology, this is a technology that is around, it has been around, it's relatively new, maybe 10, 15 years that we have them in practice. The impact is, actually what it does, you can make sensors using the same technology that you built ICs. The effect is, you can make them much smaller, much cheaper. That's it. So every single cell phone that you have, they have these type of sensors, MEMS sensors. Previously, that's magnetometer. You have it in your cell phone. But this is the one that you have. This is MEMS technology. You have accelerometer. These GPS, these location positioning, they use these type of sensor. You don't use this sensor. That was basically an accelerometer maybe 15 years ago. So the cost obviously much higher. You reduce the cost, you reduce the size. So every cell phone that you have right now have many sensors like this. Now, I have to speed up. So sensors, MEMS sensors are almost everywhere. We have them for medical application, auto industry. We use them for many applications, tire pressure, airbag, brake sensor. All of them are actually sensors are MEMS technology. Now, there is one problem with MEMS technology. MEMS technology is not easy to integrate with the current IC technology. So it is, you have to fabricate MEMS, and then you have to fabricate IC, and then pack them together. That's one of the problems we have. So, and one other thing that I haven't mentioned is, if you compare the cell phones or the computers that you have had 10 years ago, and you compare it with the current available PCs or cell phones, you see a huge improvement, right? A considerable improvement from 10, 15 years ago. The reason is CMOS technology. The reason is every 2 years, we can double the size, we can reduce the size and double the intensity. That's the reason that you see these progress, huge progress in the area of technology. For example, you have USB, right? You recall it, USB memories. A few years ago, they were, let's just say, 1 gig or 500 meg, something like this. Now you get 128 gig, the same size, right? Why? Because we can reduce the size of the transistor. And this is the driving force in our design for cell phones, for every electronic related. Not only these requirements, these specifications, but also this technology, what is nice about it, it doesn't consume battery. So static power consumption is almost zero, okay, very low. So these are two main advantages of CMOS technology. We can scale them, and that has been the story since 1970. Every 2 years, you double the number of transistors, double the processing power, reduce the size by 2, and it's an ongoing story. But we are closing to the end now. We see that it's slowing down, okay? We cannot move with the same speed. So splice scaling has slowed down. Static power is not negligible anymore. That's the limitation of the technology that we have used for many years. Now I show you the current two-dimensional CMOS fabrication. We just, the current technology, and then you have a silicon, you polish it, you go lithography, you just separate the ICs and you put them in a package and then use them. The result is these kind of sensors that are available in the market. So you put these ICs and sensors to a PCB board, and then that's a system you have. What if you put them on top of each other instead of putting them close, right at the left side, at the planar? Now, what if you put everything on top, make it 3D? What would be the advantage? The advantage would be smaller size, lower power. The idea was there for 50 years, but we didn't have the technology to do it. Okay, now we have the technology to build 3D IC. The result is lower power, higher speed, almost everything that we are looking for many years. So let's just see. Right now we have these type of ICs in the market. It's called 2.5D. So you put the dies, the silicon, on one chip and then connect them from the bottom together. So that you reduce the size to a certain degree, but still it is not 3D, because 3D you expect to put them on top of each other, so layer by layer. And the technology that was not available is this technology, these small wires. You can believe in this. The wires that connects the top and bottom together, the diameter is 5 micrometer, the length is about 50 micrometer. And for 50 years, we couldn't build them. Okay? For 50 years, we knew, but we couldn't build them. Now, this small technology, that's a wire, this is just a wire, 50 micrometer length, 5 micrometer diameter. But you have to build them in such a way that's reliable, right? You don't want to put them over there and then after 5 days, 10 days, then the system doesn't work. So you need something that's reliable, and you need thousands of them, okay, when you put these ICs on top of each other. Because you want to connect top and bottom together, okay? Now, these are available technologies. These are what we actually currently use, and this is the emerging technology. Okay, this is the one that what we call it, these small wires, we call it TSV, through silicon via, to connect the top and bottom. So if we connect these top and bottom together, this is the kind of system you are going to have. You're going to have sensors, maybe chemical, biomedical sensor. You may have image sensor. You may have nano devices. You may have RF, wireless link. You may have static memory, processor, energy, everything on top of each other. So you can imagine that you will be given a cube of, let's just say, 3 millimeter by 3 millimeter by 3 millimeter. It includes everything. It has the processing power, everything other than power. Power is still, we have a problem other than the battery. So if we successfully implement, use 3D IC technology for sensor implementation, we reduce the power consumption. That's very important. So the sensor that I talked to you, it works for a year. Now with this technology, probably it can work for 2 years or 3 years, okay? At least 2 times the length of the lifetime of the power, the supply, the battery. Integration of different technology. I told you that the CMOS and MEMS technology. MEMS technology is the MEMS technology is the current technology for sensor fabrication. I told you that these are not so compatible. Now, it doesn't matter. Fabricate this one in one technology, fabricate this another one, and then put them on top of each other. Connect them to each other. It doesn't matter now. Now, hardware security. Hardware security, I talked to you that's very, very important, and on top of everything. Now, you have processing power. You can add, and every layer that I'm talking about, every layer is 20 micron. Imagine, 20 micrometer is every layer. So you put on top of 5 layers of processor, which actually guarantees the security for your system. It's just 5 times 20 micrometer. It doesn't matter. Okay, just put them on top of each other. And reduce, obviously, physical size. So you reduce the size, you increase the security, you integrate different technologies, and reduce the power. All of them are the advantages of the 3D IC. There are certain challenges, obviously, how you test such an advanced structure. Test becomes a problem. And then thermal management also becomes a problem now because you condense almost everything close to each other. The power, the heat generated there is significant. So we have to figure out how to get rid of the heat because otherwise the fatigue and the effect on the circuit will be significant. So the conclusion, TSV-based 3D IC technology provides a platform to integrate different technologies. That's one thing. Hardware resources for security algorithms can be integrated using 3D IC technology because it's just you add few layers. And 3D IC technology reduces the length of interconnects and consequently lowers the power consumption. So that's also very important, and it can reduce the physical dimensions of smart sensors. With this, I conclude my presentation. If you have any question, please. Thank you. Any question? Yes.
I talk with the 3D sensor, but the important from 3D sensor is that's how we can align and fix this all of the layer together. Alignment and fix it together because 2D, okay, we can just align and we can do the math and we can design a lot of the channel or a lot of device on the plan, right? But the 3D, you are fix this layer by layer together. And with you taught me that with the technique about the 25 nanometer, it's a silicon. Yes. How we can align and connect it together in the channel?
We have the technology available here right now, okay? If you are familiar with the props that we currently have, the resolution is 1 micrometer. So we can move them 1 micrometer by 1 micrometer in any direction that you want. So then you can put them on top of each other. In addition to this, you can actually add some pins to make sure that they correctly align on top of each other. So this is technically, it may seem a little bit difficult, but it is a solved problem. We don't have that much of a problem to put them on top of each other because the machines are already there.
Okay.
Okay.
Thank you.
Any other question? Okay.